Right, so we are learning about the epidemic models, and we saw SI and SIR model in the previous class. So today we will look at another model which is similar to SI model. It's known as SIS model. So as the name suggests, you have susceptible individual, and then you have infected state, and then again susceptible, which means that you have somehow you lose the infection. You are infected, and then you again become susceptible, right? You don't acquire any immunity in this process. In the process of infection, you don't acquire any immunity. There might be some infection which doesn't generate that kind of response. More often, for example, you can have certain kind of skin infection which reoccurs again and again. You can have, for example, take the example of dandruff, which is fungus plus microbes, and it reoccurs, right? You use certain medicine, shampoo, it goes off, and then again you get infected with it. So there are a number of contagion which may follow SIS model. So a susceptible individual goes to infected state with the rate beta. Beta is the transmission rate, and likewise from infected state, the individual goes to susceptible state again with the rate gamma. Okay, so accordingly we write ds by dt. This will decrease, of course, beta sx. And since it is also accumulating, the infected individuals are now becoming susceptible. So we add gamma x, right? Plus gamma x. And likewise, we will have dx by dt, which is beta sx, and then minus gamma x, right? So again, you will have s plus x is equal to 1, right? You can put this value here. Let's say how the x changes. You have beta 1 minus x here, x minus gamma x. You can also write it as beta minus beta x minus gamma x. Right? Now this equation has a solution which is very similar to what we saw in SI model. So this has solution which will be xt would be somewhat proportional to, I'm not writing the exact solution now, this will be proportional to e raised to the power beta minus gamma times t by 1 plus e raised to the power beta. There will be other constants also around. Okay, so that's why I use proportionality. This is not equality here, which will have solutions similar to what we had in SI model. Now, if we plot this trajectory for x as a function of time, you will see that it follows the same trajectory as in SI model. The difference is following. It will, since there is gamma here, it will never reach 1. Okay. So the complete population will not be infected at all. Why? Because there are individuals who gets infected and they again come to susceptible state. If you make gamma 0, which means that if you have gamma 0 here in this equation, then this equation becomes like a SI model, and then this will go to similar to what we had in SI model, right? So this is your SI and this is your SIS. But this never goes to 1. The whole population never gets infected if you have reasonable amount of gamma. Right? Now this tells you another thing. Now you can find this size also, this epidemic size x at saturation. from this equation, right? So you can find what is the epidemic level, what is the epidemic size. So again, at the saturation, you have dx by dt 0, and then you have beta minus beta x minus gamma, right? So this x also becomes 0. So now you can write x from this equation, which will be beta minus gamma. So beta x goes on this side, right? So this is beta x, this is beta minus gamma. So you can write that x is equal to beta minus gamma by beta. Does this make sense now? This is the epidemic size, and it really makes sense because you will have a reasonable size of epidemic if beta is quite bigger than, if beta is sufficiently bigger than gamma. And if beta is actually less than gamma, then this will die out, right? So this epidemic will not take this shape, this will just die out, right? If beta is less than gamma, then this becomes, in fact, this will die out at the transition point, which is beta is equal to gamma. So this becomes 0, so the whole thing becomes 0, so there is no epidemic. So again, epidemic is decided by beta and gamma. If these two quantities are same, which means that beta by gamma is equal to 1, then this is your transition, epidemic transition. Above this is your epidemic, and below this there is no epidemic. Right? So this is your SIS model, and there's another model which is SIRS model. These are basically extension of SI and SIR model, where we lose the infection or the resistance for the recovery, right? So SIRS model, you have states S is getting infected, and then it is removed either by recovery or death or resistance. But then this resistance is again lost over time. In some cases of COVID-19, we know that there are reinfection, right? So recovered individual is again susceptible to infection, but it happens rarely in the case of viral infection. But in some disease model, this might be true where we lose. So a lot of the antibodies that we generate after vaccination in our childhood, 10 years, 15 years, 20 years down the time, when people test the level of antibody against that antigen, there is none. Okay, so over the time, given the sufficient time, we lose immunity, right? So this is not completely impractical model. It does happen. So if you model it in that way, now the problem with this model is there's no unique solution of either of ds by d. So you can write now, this is your beta, this is your gamma, this is your delta. So you can write it now. So your ds by dt is minus beta sx plus delta r. Let's say this is r, this is x, this is s, plus delta r. Dx by dt is beta sx minus gamma x. Dr by dt will be gamma x minus delta r. Now it turns out that if you try to take these quantities and try to get the solution, get the analytical solution, we don't get a unique analytical solution. So people try to solve this model using methods popular in the nonlinear dynamics. In the field of nonlinear dynamics, there are some methods that we use of nonlinear dynamics to get the solutions. But even there, you have very diverse behaviors. Okay, we don't get a, for example, in the earlier models, we saw that there is a kind of, at least qualitatively, curves are similar, right? So this curve will be like this. This is a trademark curve of SIS model, and this is the trademark curve of SIR model. Likewise, you have SI model. The trademark curves, which will quantitatively change in the y-axis, but qualitatively they will be like that. But we don't have such unique trend that I can show you here. Right? So we do not have. This is a kind of difficult model to be solved. It gives you different. It throws different patterns with different values. So even not only quantitatively, qualitatively also the curves will be very, very different. So this is not very popular method. Okay, so now the important point. We need to look at the network description of model. So let's say network description of epidemic model. So let's say I start with SI model. So in the previous classes, we didn't invoke the network thing, right? So the moment I say network, I mean the adjacency matrix. So what if I invoke network structure in the SI model? How can we model it again, and what is the solution? So it turns out that it's not very difficult. What we do, for example, in SI model, we had these quantities S. We have this S and X, right? We change these quantities instead of number or fraction. We change it to the probabilities now. So what we do, the first thing that we do is the SI, we say, is the probability of node I or individual I to be infected in some time interval, right? In some time interval, let's say from t to some t, delta t, right? So likewise, you have xi is the probability of node I. Sorry, this was incorrect. This is to be susceptible, right? S. This is for infected state. Right? So now we change it to the probabilities for each node. Now the question is, we need to find out what will be dx by dt in this case. So let us define that now. How can we define dxi by dt? So the first thing is that, of course, beta is again there. Right? Now here, let's say, okay, let's start with the SI first. Let's start with DSI. Change in the probability to be susceptible for node I. Now, of course, the beta is still there, okay, which means that we still have a disease transmission rate, which is basal, and quite often what happens that disease transmission rate beta is different for different contagion, and which is largely like a constant value. More often, not entirely, because, for example, COVID-19, when it mutates, the disease transmission rate becomes higher or lower and so on. But let's say for one particular strain of a particular contagion, this is beta. So we, again, of course, this is going to be minus beta times something, right? Now, minus beta times SI remains same. That what is the probability that it is susceptible? If you, so of course, so what was the probability to be susceptible times? See, a node has to be susceptible to get infection. isn't it? So I think earlier thing was fine. Let us first understand the xi. That would make sense. My God, the eraser feature is really bad here. Anyway, so this is dxi. So the node has to be susceptible first, right, to get any infection. So this is similar to what we did beta Sx earlier in the earlier models. So there it was a fraction, right? Now we say the probability. So there will be some susceptibility probability of node I. Now it will, so to acquire infection, the node I would interact with other nodes in the network, right? So we need to get what is the probability of infection of its interacting partner. Okay, what is the probability that the interacting partners of node I are infected? Some of them will be infected, others are not infected, right? So we need to find out what was the xi value of those nodes. So since we have already used the I index here for the present node, we use the j index for the other nodes, right? So then we sum it up. For some individuals, for some of the friends of node I, will have low probability of infection. Xj value will be small. For some, it will be large. So we need to sum it up, right? And how can we sum it up? We use adjacency matrix there. So we sum it up over j, aij times xj. Right? This is the change in xi. Now what you can do is, again, in this case also you have Si plus Xi is equal to 1. So what you can rewrite it in terms of 1 minus X here, Xi here. And likewise you will have dSi by dt will be given by minus, so sorry, this was plus here, right? So now we have number of susceptible individuals which will decrease. So we have a negative sign there. So these are essentially the same. These two equations are essentially the same, right? Now, in this case, what we rewrite is this one, 1 minus Sj. Right? So this is in S form and this is in X form. So we are more interested in the change of probability of infection, right? X. So can we write this in the form of matrices now? We have a problem here in this equation. We perhaps particularly in this equation instead, to get the matrix form, to get the some derivation for some convenience, we are making an assumption. Now the assumption is of early times. Let me write it. Here are the assumptions. We are making the assumptions of early times of epidemic. Early times. So in early times, what happens? What will be your xi value would be will be very, very low, right? So n, given the n is very large, we say that Si approaches to 1, right? So we actually get rid of this. So if we do so, what happens is the following. I can rewrite the whole thing in the matrix form now. X is a vector here, vector of infection probabilities, right? Is equal to beta, which is a constant scalar value. A is the matrix, right? And then we have X. Now you might say that we are again leading up to something which sounds familiar, right? This sounds familiar, but now it's not straightforward to get the solution. What we need to do is, let us say that I express the vector x, which is the vector of infections, right? So let us say that I re-express the vector x in as a function of, as a linear combination of, let's say xt. This is vector, okay? So this is a vector. Is the linear combination of the eigenvector, so eigenvector of matrix A. So I am using certain scalar values for the linear combination at time t times VR. V is a vector here. So I'm taking a uh, various eigenvectors of matrix A. So this is the eigenvectors of matrix A. All right. So I'm re-expressing vector x in the form of linear combination of eigenvector of matrix A. Now you might say, can we do that? Anybody, can we do this? We have done it, or I didn't make any assumption here that this is the linear combination of eigenvector. X is the linear combination of eigenvector. I didn't make that assumption. This equality holds. Anybody? How is this true? And why is this true? First of all, why is this true? Okay. We know A is a symmetrical matrix, right? Isn't it? And the eigenvectors of such a matrix would be what? Let's say two of the eigenvector, eigenvector 1 and eigenvector 2. What is the relationship between the two? See, these eigenvectors, it should be clear to you people that these are orthogonal, right? Now, can somebody tell me, I have answered the first part of the question. This is true because these vectors are orthogonal. The second question is, how is this true now? Can we have some example or derivation for that? Well, simplest thing you can do is, let's say there is one vector. I'm taking a very easy example. One eigenvector which is 1, comma 0. There is another one. Well, these are, let's say, column vector. I'm writing it in that way. Is 0, comma 1, so they are orthogonal, right? Now I say that I write another vector which is x, comma y as a linear combination of b1 and b2. So the one of the way I can write it as x times 1, comma 0 plus y times 0, comma 1, right? I can write it in this way, right? This is what? Nothing but the linear combination in the form of linear combination of the eigenvectors, right? So if you have orthogonal vectors, this is possible to do that. If we are orthogonal, this can be done, right? And if some of you are not aware that why this is orthogonal, we can discuss that in some other class, but there are tricks to show that. You can take two eigenvectors, let's say ax1 is equal to lambda 1 x1 x1, and take another one lambda 2 x2. Do some algebra with these two equations, and you will see that in the end x1 x x1 transpose x2 is going to be 0, which means that they are orthogonal, right? So anyway, so if we express it in this form, what will be my dx by dt? So now my dx by dt becomes This is a vector, okay? It's not a scalar value. Now we can also get this in this form. So this equality is obtained from this equation, and I'm going to write another one which will be obtained from this equation here. So that can be done by writing it as beta A, and now we have x there. We write summation over R because that's what we have. X is equal to in terms of AR, right? So I'm using these two equations now. Okay, so there is the one thing that you need to, there's a trick now that I'm going to use. I'm going to change this equation. I have A here and I have VR, which is the typical your eigenvector function, the equation that we know, right? So we change it to in the form of eigenvalue times eigenvector. The way we do this is this becomes beta. Let me use the same color. Let's say I write the eigenvector as kappa r, and then we have AR P times VR. Now here is the trick that we will use. We will try to find out the common things in this equation and in this equation. So let's try to find what is common in this equation and in this equation. Summation over R is common, right? This is common here. Summation over R is common here. And VR is common. VR is common. So which means that I can express dAR by dt should be equal to KR P, right? And beta, sorry, beta should also be there. It's not common in the both equations. So I know this this equality holds, right? So from by comparing this equation and this equation, I found that this equality holds. Now what we can do is we can put this value in this equation. Okay, so in fact, before putting it back to the xt to get the xt value, what we can do, we can actually get the solution to this equation, which exists, and some of you can also guess it. The solution to this is going to be a at time t is going to be a at time 0. Sorry, this is AR at time 0 times e raised to the power beta times kappa r times t, right? This will be the solution of this equation. Now we can put this into this equation. All right, so if we do so, we get the following. We get x p is equal to summation over r AR at 0 e raised to the power beta kappa r t times vector VR. That's the solution to xt. Now, the leading term of this equation would be determined by the leading eigenvalue and the leading eigenvector. So xt can actually be simply approximated. This can be approximated to e raised to the power beta k. So leading eigenvalue, I'm writing it as k1 times t times v1, which is the leading eigenvector. Now this will look like very similar to SID. If you plot this solution, this is very similar to what we see, the trajectory that we see in SI model, like this one. However, now it is not only dependent on beta, it is also dependent on the network parameters, right? The network parameters here are K1, which is the leading eigenvalue of the lead eigenvector of adjacency matrix and the leading eigenvector. Okay, of course, you might say that other eigenvectors also have contribution, but we have simplified that. So this is approximation, not the exact solution. So you will have contribution from the other eigenvectors also. What does it tell you? You need to bother about network structure, and you just need to look at the leading eigenvector of eigenvalue and eigenvector. And what is this? You already know the lead eigenvector of adjacency matrix. This is leading eigenvector of A. What is this basically? Sleeping. What is the leading eigenvector of A? That is nothing but the eigenvector centrality, right? So where are we leading to? We are leading to a fact where we know that the leading eigenvector or the eigenvector centrality of a network is in fact a rough measure of probability to get infection. If you have high eigenvector centrality, you have higher probability to get infection. Right? So it's not the degree thing, it's the eigenvector centrality, not the other centralities. Eigenvector centrality is very important. If we know in a social network eigenvector centrality, we roughly have the measure of infectability of each individual. This is important derivation. I do not have any other thing in SI model. This is your SI model on top of network. Now, okay, mathematically, whatever we have done is actually not the perfect thing. We have done approximations here. The first thing that we have in this approximation is this assumption that we made is the early times, right? Now, the late times, we are looking at whatever we got in the final equation. This is the behavior of early times of the epidemic dynamics. What happens in the late times is not covered in this equation. One has to do independent derivation for that. So this equation is not the exact solution. This is some kind of approximation just to display, just to show that this quantity is a rough measure of infectability of individuals, which is very important. So you have seen in this course again and again and again, we land up to eigenvectors. So it's a very handy thing in network science. It has a lot of applications in whether we are talking about the structure, the dynamics, or dynamics on the network. We land up to eigenvector every now and then. Now, okay, so what we will follow now from here is we will look at the SIRS model in terms of adjacency matrix. And we will again see that it actually follows the typical, sorry, this is SIR model. This will follow the typical SIR model, the overall dynamics. But again, through some approximation. Okay. Yeah, so that was all for today. Any question? Okay, so you might be wondering what is happening with the epidemic threshold here and the R0 value in terms of network now. That will come in SIR model. So we will see that once you invoke the network structure in the epidemic model, there are additional factors that we need to bother to calculate the R0 value, right? Not only beta and gamma, you have one additional factor, and that factor is already visible in this equation. But right now, I'll not discuss about that. We will discuss in the next class. So the R0 value differs if you invoke the network structure. And in fact, you get more precise value of R0 if you know the network structure. That has been missing in all this COVID-19 analysis and so on. If you are comparing countries like Italy and India and all, then R0 value, what you are observing is the observation, is the outcome of what is happening inside the system. And that cannot be generalized. Okay, so we can't generalize what is happening in Italy or UK with the what is happening in India, because network structures are radically different in these countries. So although they would have calculated R0 value based on the confirmed cases, we would have calculated R0 based on the confirmed cases, how it is spreading, some approximate R0 value. But these two are determined by the structure of the social context that we had in different countries, and which is radically different. Right? So even if we get similar R0 value, that doesn't mean that the determining factors are same. And R0 value has to be different in different countries. One thing which is missing in all these models, whether the network structure is considered or not considered, is the how immune is the population is, right? So this model, if I implement on Indian population, it will show certain trajectory. If I take the same kind of network structure in China, okay, which is also very dense, and do it, I'll get same trajectory. But if one of these populations are having cross immunity from other viruses, trajectories will be different, and that's where observation comes into play. Models remains model, and they are dependent on parameters. So until we have that immunity parameter plugged in, okay, we cannot capture what is going to happen. Okay, which is why a lot of these factors, for example, the network structure was not invoked in COVID-19. I haven't seen any good paper on that. There might be some papers now. And then, although that could have been mapped through multiple sources, and then the population differences, okay, and that population differences not only depends on the cross immunity, the age. If there is a particular, for example, Italy, you see a lot of lethality there because of aged population there. What has happened in Japan is completely mystery, a complete mystery, right? We didn't hear much about the panic situation in Japan. Was it controlled, or what has happened? So there are too many parameters, and considering all of them, when we do not understand how the virus is functioning, has led to models and predictions which were damn wrong. Okay, many of the, almost all the models, predictions that were made about COVID-19 in each of the countries were wrong, because this is not, this doesn't remain as a mathematical model now. Okay, now onwards, after COVID-19, you will see a surge in epidemiological studies which are data centered. Okay, people will start gathering data sets to actually come up with models and learn about new parameters which are missed, and you can learn those parameters through machine learning. Okay. So that was all for the day. In the next class, we will look for SIR model on the network. And then what is left after this is the algorithms, some of the algorithms, how do we calculate, what is the complexity of eigenvector, or let's say betweenness centrality? When we do that on computer, what is the complexity? And likewise, what is the algorithm for shortest path calculation? So once we are done with that, then we will see individual topics, okay? For example, the metabolic flux analysis, controllability of the networks. Somebody mentioned that Hill's equation, if I can have a class on that, I will have it, one class on gene regulatory network. So those will be individual additional topics. Okay, and then we'll see how many classes are left and decide about the journal. All right. No questions?